Okay, hi everybody. Thanks for coming. Welcome to the next seminar in the Robot Learning Seminar Series. So I'm very happy to introduce you to Nathan Lepora, who's a professor at the University of Bristol, a professor of robotics and AI. So I've known Nathan for a few years, and I first got to know him through these optical tactile sensors that he developed. So these are tactile sensors with little cameras inside that allow robots to essentially see the world via little cameras that observe deformation of tactile skins. And I borrowed one of these and did a project on it, and that was my own introduction to tactile sensing. So everything I know about tactile sensing is through Nathan. It's great to have him here today. And he builds stuff. He gets his hands dirty, physically builds new sensors, whereas I just buy stuff, and sort of see what I can do with them. So he's a proper roboticist. He builds robots, puts things together, puts together full systems. And thank you, Nathan, for coming, and over to you.
Well, thanks, Ed. Thanks, everybody, for being here. I don't know if this microphone is a bit too much. I think it's a bit too much. It gives a bit of an echo.
Maybe
so
we don't need it.
I'll put that.
Yeah.
That's better.
Okay, yeah.
Okay, so I kind of build things vicariously now, as we all do for us students. I have built a tactile sensor in the past once. So as Ed was saying, it's a dexterous tactile robotics. That's kind of what I do, what my group does. Things I like to do is in our group we like to build the sensors ourselves, and we like to build the hands, things to put the sensors on. We'd like to integrate those sensors we build, tactile sensors we build, into robotic systems, robot arms typically, and then we like to do the control as well. So you've got a complete system there. I say my lab specialises in tactile sensing. I see the point of tactile sensing is as an enabler for dexterity, to get robots to move, to physically interact with their surroundings. So I feel you need to do all of that in order to, properly push forward tactile robotics as a discipline. So I will move on then. So this is the group which I built at BRL, Bristol Robotics Laboratory. So it's now up to 2020 or so. It's just me, and then fortunately Ben, who was my first postdoc student, he's a lecturer and research fellow. Effie, she's a postdoc with me. She's a lecturer now, and actually we're partnering many grants in terms of we're co-investigators on a few grants now. And then Tanya's joined our group. So there's four of us. They're kind of a cluster of interests in dexterous robotics. At BRL, there's also the UE side. I also work with soft robotics, like Jonathan Roster as well. And then at BRL, there's a UE side. And there's a teleoperation group led by Charlie with Ning and Zed. Charlie's actually just been poached by Liverpool or Manchester, I forget which. So there's no Charlie anymore at the University of BRL. He was a prolific paper writing machine. He's one of these people who produces about 50 or 60 papers a year. So he's gone off to Liverpool now to do that. And then there's also Martin Pearson, who's led on the whisker box. I don't know if you've seen this robot. It's a rodent robot with tactile whiskers. Tactile. Okay. These are some things that have been happening around tactile sensing, robot dexterity. So, in my view, the field has taken off. When I was first appointed as a lecturer about a decade ago, I kind of positioned myself in an area which I thought would take off in 5 to 10 years, because I saw it as a key component of dexterous robots, and now that's happening. So I'll show you some work from other groups as well as our own. And then there's initiatives relating to that. So 2010, there was a very influential paper, review article on tactile sensing by Ravinder D. here. It's still the leading review, and it marked kind of a turning point in the field where perhaps tactile robotics wasn't so well, in kind of a bit of a dead, a quiet zone, and then the field has kind of taken off since then. And so I'm an editor on a new special section on tactile robotics. It's in transactions and robotics. That has had hundreds of submissions, so we're currently working through as editors, wading through that a huge amount of papers. The other thing that's been happening is the UK manipulation, which obviously Ed's been instrumental in having that take place. and it was here 6 years ago. So we had it in Bristol about a year ago. So 200 people came to that. It's quite impressive. I think it exceeded all of our expectations. And then it's been at Oxford this year. So I led it along with Effie. And then this year it was in Oxford. That's not working. And I think there's probably about 300 people. So I think that shows, the interest in the UK in robot dexterity. Right, okay. So onto the science and engineering. So I guess you've all seen this. It's looking a bit out of date now that Boston Dynamics came out with their new Atlas a couple of days ago. So, anyway, Tesla robot, Elon Musk, lots of money being put into this. So the good thing is, from my perspective, it's got tactile sensors on it now. Yeah, so they're recognising the importance of tactile sensors if you want to have a dexterous humanoid. Okay, so we all know about this. So there's a lot of money going into humanoids at the moment. Figure, I think, got 700 million investment. You could say over-investment, So, so anyway, given this is, so clearly.
Do you know what type of tactile sensors they've got?
Yes, because I wrote a reference letter for the guy who got the job there. It's a magnetic one, basically. If I can dig out the guy's name, he's got papers on it. I'm going to criticise them in a minute. Well, they're not bad, But I think the summary of this is it's not bad. Yeah? I think it's things I think Tesla got right and wrong. So these are personal opinions. You don't have to agree with me. It's just what I view. It's my view. In my view, dexterous hands are the problem to solve. So why bother with the rest of the humanoid? Why not just put that 600 or 700 million into building better hands and arms, get them to do the dexterity and forget about the humanoid, solve that problem. It doesn't really matter what you put the hand and arm on. The rest of the humanoid is just a robot for getting the hand and arms around. Yeah? Perspective? Some people disagree with me on this. I gave this talk at IIT, and Lorenzo Natale, who's one of the leads on the Optical project, he agreed with me. He's the lead on the Optical, but it's a problem leading humanoids in Europe. And his perspective was actually the hand and arm system has as much complexity, or if not more complexity, than the rest of the robots combined. Or at least in humans. And if you look at our brains, there's as much of our brains for hands and arms as there is for the for the somatosensory system for the rest of the body. Okay, so tactile sensors are a good thing, but it's a low resolution tactile sensor. It looked blocky. It's not a high resolution tactile sensor. And the big change in the field is that it's towards having high resolution, high information content, particularly on the work that's doing dexterous control. But still, it's a good thing that they're doing it. Now they've got under-actuated hands, so each finger looks to be individually actuated with a motor forward and then motor back. So it's like 10 motors, 10 degrees of actuation. There are better ways of doing this. You can get better dexterity with fewer motors, depending upon how they are, wired to the hands and tendon, on your actuation system. But anyway, all this is a step in the right direction, but they're probably, in my view, 5 to 10 years behind, the state of the art. But I'm sure they will, adopt these things next. Okay, and this is the point on the actuation. So the left robot hand is the PISA IIT soft hand, and the right one is shadow hand, which I'm sure everybody's heard of. So they kind of look similarly dexterous. You can see the shadow hand can do a bit more, but actually the PISA IIT hand is doing more diverse tasks. It doesn't look that far behind in its dexterity. The PISA IIT hand has one motor in it, but the way that motor is coupled to drive the fingers is done in a, if you like, sophisticated way. Whereas the shadow hand is 24 motors, basically one motor per joint. Yeah. It means a big difference in its cost. The shadow robot hand, as we all know, is very expensive to the degree that most academics can't afford to buy one. Whereas PISA IIT hand is affordable. And then there's other issues to do with control and so on. But this is just to show that the design of the hand is important as well as the intelligence and how you control it. Okay. I don't know why this keeps. So I got into building robot hands about a year or two after I set up a lab, and the idea was, because I deal with 3D printed tactile sensors, the idea was to do 3D printed hands with it to go together. So we started off with the Yale Grab Lab hands, which won the DARPA Grand Challenge. The Model O won the DARPA Grand, and actually Ad is from that group as a postdoc. And so we started off with the Yale Grab Lab hands. So they won the DARPA Grand Challenge back in 2013 and open sourced this hand. That's the hand I wanted to get to. It basically took two PhDs to get to that point. It's not hard. It's not easy building hands. But so we've integrated tactile sensors with those hands. And in 2019, I switched to working with companies. One, PISA IoT, who have commercialised their hand, and then I also worked with Shadow. Let's just say, last week I was giving talks at PISA and IIT. I can't remember the last time I spoke with Rich. And also, one paper that was very difficult to publish on this, and we've got quite a lot on this, 5 to 10 papers. It's an area that's growing in my group. And these are some of the kind of things we do to put tactile sensors on it. You can pick stuff up and recognise what the things are, recognise if it's a stable grasp just from touch. Label data, you can throw it into a convolutional neural network, etc. You can predict things once you've got the labels. Slip detection, you can do picking things up and having robust grasps. Picking things, delicate objects up, and this is actually one of the studies we got with the Shadow hand. This is kind of an in-hand dexterous controlling something for a sensor. These are the kind of things we did with the hands. Tried messing around with soft grippers as well, so putting fingers on a tactile, pneumatic fingers, or this is a pneumatic higher degree of actuation hand. Both those nice studies. This has just got accepted in transactions and mechatronics. This is finding its way through review. So it's all good. It's interesting stuff. I was particularly into this study. I liked it because it's simple. The issue I found is once we started dabbling with soft robotics, I see Thrish isn't here, so the students didn't want to work on it anymore afterwards. They finished this project and they were kind of felt it didn't really take them anywhere. There was nothing really to build on afterwards. So they didn't want to work on this. They wanted to work on a different project with more conventional kind of robotics instead. I mean, and so I say I was really into this, but it was the students' reaction. Both cases, in fact, one case the student actually left our group and moved to another group, to Shan's group. As I say, yeah, and it's just. So I really like the technologies, but as I say, the thing is, it's kind of hard to bring it. In my view, it's hard to bring it up from a kind of TRL 0 kind of level. As a group, you want to keep building upon things, and I found that easier with building the other types of hands that are closer to commercial application. So this is where we're going. I'll discuss a bit more about the Allegro. That's the Allegro hand. That's the hand, the fully actuated hand that we've bought now and we're using. I'll show that a bit later. And then we've got a 3D printed version of the PISA IIT hand that we've developed with PISA and IIT, which we call the BRL PISA IIT hand. So the point of A, I like 3D printing, like to build our own stuff. B, it means we can integrate it with our tactile sensors a bit more easily. And C, it means we can add more degrees of actuation to the hand because we now have control over the design of the hand. So the first extra actuator we added was to put an antagonistic tendon system on there, so you can both close it and open it, and variable stiffness, so on. So that's just finalising, and then we've got another version. Basically, the game is we add more degrees of actuation to a hand. If you've got a hand that's already got dexterity because of its design, I see adding more actuation to that to improve its dexterity. I see that as a way of getting kind of meaningful dexterity, rather than sort of going with something like a fully actuated hand, like Shadow hand, and throwing all the AI methods you can think of at it and trying to get dexterity out of it that way. It's a different approach, but anyway, this is kind of work that's ongoing. Okay, so I'm going to move now to sense of touch. There's a bit on the hands, because that's, say, my group also does some hand design as well, and also does some integration of tactile sensing into commercial hands. So human-like hands need a sense of touch if you want them to have dexterity. So artificial touch has been around since the 1960s. And it's one of those technologies, kind of like nuclear fusion, where it's always like 10 years away from becoming, mainstream. But now well, that's what's been said again now. Maybe it's now 5 years from becoming, ubiquitous. This is from the 1980s. I mean, you can already see as a tactile-based display, it doesn't look that different in terms of performance from what was on the Tesla robot. It's got about the same resolution. Sense touch biotap, that was very important across the 2010s because it's basically it's quite expensive. It's £10,000, $10,000 a fingertip, but it was bought by many academic labs and kind of had a standard platform. Quite low resolution though, 24 tactiles. It's not state of the art now, but was important for its time. And then just to say that many of the people are well known in the field, like Paolo Dario, Danilo De Rossi, even Mark, guy who did Boston Dynamics, Mark. So these were all working on tactile sensing in the 1980s. Yeah, that's kind of how you get, and then they moved out of it when the field didn't really. I mean, it's too soon, I think, for the field to really be appropriate for dexterous control of robots, which is where they all wanted it to go. Okay, so what's changed recently, the last 5 to 10 years, in the area I'm working with optical tactile sensors, as Ed was saying, so there's many different transduction technologies been tried out, electronics, piezo-resistive, and so on. But about every kind of electronic transduction you can think of has been tried in tactile sensors over the last 60 years or so. One of the types is to use a camera inside the tactile sensor, because produces a high resolution camera output and basically image the inside of the sill. And the big change is because of Moore's law, cameras are now tiny. And also, laptops, phones, commercially driven cameras to miniaturize inside and become more high resolution. So this is 3 years ago. This camera, which is a grain of size of a grain of sand, it's now probably a UHD camera. For sure, we were buying these 3 or 4 years back because we wanted to shrink our tactile sensors to the size of fingertips. And this is the key technology for doing that, the miniaturization of the cameras. We were paying £1,000 a camera then. We're now paying $10. Well, we're buying it in China, but roughly $10 a camera. That's really small now. And that's the big change and in my view, that's happened. That's made optical tactile sensing, the right technology for the next 5 to 10 years. Who knows what will happen after that? Maybe there'll be other technologies. But at the moment, this is the only viable way of getting, cheap, usable, high-resolution tactile sensors, in my view. So the leading ones, so the gel sight is most well known. It developed at MIT. It's been used at a lot of other groups in America, and like Shan here as well develops those as well. And then I would say ours is reasonably well known as well in the field. Not as well known as the gel sight, but we were one of the early ones as well in the area. Got a review paper that's quite well cited. I can see the influence in the field from our work on it. Principal difference is the gel sight is it uses photometric stereo. So basically, it looks at shading on the surface, on the inside of the surface, from LEDs that are different colour LEDs that shine. So it's basically looking at shadows and illumination. So in effect, it measures indentation, whereas ours has these. I can pass some around.
Let's grab a few of these. Thanks. Cool.
Please be careful with this because the skin's falling off.
Are these the same? Oh, this is just a miniature version.
Yeah, various versions of it. So ours has these pins on the inside, and then what we pick up with the camera is the movement of the markers on the ends of the pins. So we're actually more sensitive to shear. the pins you can think of as a mechanical lever. They are levers, and then what they do is they amplify small amounts of normal indentation into larger amounts of shear. So they're a mechanical amplifier. So it means what our sense is more sensitive to shear, for sure, than the gel side. But the gel side is, say, really, really sensitive to indentation and getting an image of the shape of an object. And our sensor has this mechanical amplification, which I say means it's very sensitive to small forces as well, which I'll come back to later. So altogether, so it's soft. It feels quite spongy. The gel site is actually quite rigid if you feel it. Also quite soft if you feel them. 3D printed, and it's biomimetic because this pin structure is based upon the structure of human skin. There's these structures known as dermal papillae, which are sitting between the more rigid outer layer of skin, the dermis, and the softer inner layer, that's the epidermis, and the dermis on the inside. So they have these, and the mechanoreceptors in human skin are found near the dermal papillae. So what we do is we mimic those with markers on the end that are picked up by camera. But the mechanical amplification, and the structure by which contact is transduced into signals is biometric between our sensor and human skin. This is an example. I'll pretend that I'm feeling something. So the left image is what we kind of see. This is quite an old sensor now, so we have ones now with like hundreds of thousands of markers inside it. And then the right image is basically it's Gaussian kernel density method. It's a few lines of Python. Basically what it's doing is looking at the density of these markers. So when they bunch together, it goes red, and when they spread apart, when you press on it, it goes blue. And so what we see here is we get an indentation field quite easily, but also the red bits are when we get shear on the sensor. So it kind of mixes shear and indentation up, but it's very sensitive to both. Yeah. It's not as high resolution, it's not as detailed as the gel side, but it has it's easier to make, it's more sensitive to lower forces. There are pros and cons between the two. I guess I'm taking a bit long. I'll kind of skip over this, but we did a study. I say it's based on the biomimetics of skin, the structure. We had a study where we compared the output of our sensor with some classic studies of afferents and monkeys from tactile neurons on the same stimuli, replicating the same experiments. Basically, the short story is we found a match between the signals we get off our sensor and the signals that people measure from real tactile afferents. So it's not just it's copying the structure of skin, but there's evidence there that the nature of the signals that we get off the sensor are also like what happens in real neurons. There's more subtlety to it than that, but there is a map. And so the key thing about it's got a camera in it, so it's high resolution information. I see high resolution, high information content as being important because it gives a general purpose sense of physical contact. So this is one example where it's using geometry to control the robot, the shape of the object. So that's a geometry sensor. Or this is an example where it's detecting slip. You could turn it to slip sensor. Well, this is another example. This is in collaboration with IIT, with Matteo Bianchi, Antonio Vici, where it's a softness sensor. Yeah, so that high information content allows the sensor to be customized to whatever use to utilize in whatever use you want it to do. That's why I say high resolution, lots of taxels, lots of pixels are important. I see low resolution, like the BioTac or the Tesla tactile sensor, means it can't be adapted to many other uses apart from filling an array of pressures. Okay, and then to illustrate sensitivity, we had a project with UltraLeap where we used it to measure ultrasound. So there's this kind of ultrasound haptic display, which kind of feels like somebody blowing on your hands, but in various shapes. So the haptic holograms. So it typically produces something like a 20 or 30 micron indentation of the skin. And then we could feel that with our sensor and map out the ultrasound fields. So it's feeling ultrasound midair. Other sensors didn't. They tried a load of other sensors, couldn't get anything else to work, but ours did because of this mechanical amplification We had to do some tricks with the sensor to get it to work. Weirdly enough, we're really struggling to publish this. And what's happening is the people who do this kind of stuff don't like that we can do this kind of stuff, so we're getting pushback on it from the review. They're going, oh, but you should be using, a £200,000 system, laser Doppler vibrometry, rather than our system, which costs, a few £100 or something. So the paper's still actually in review. Okay, so I'm going to move on to AI. I think it's fair to say modern AI is causing a revolution in robot dexterity. Do you agree with this, Ed?
Yeah, definitely.
Yeah.
That keeps me going. That's
Yeah.
what I'm doing.
Yeah, exactly. There'd be one people as well who's contributing to this revolution. So I think this was a turning point, or at least a marker down in history. 2019, when OpenAI used a shadow hand and lots of GPUs, lots of machine learning, very large team, basically lots of resources to be able to do this and use deep reinforcement learning to be able to twin this cube around into goal orientations. Yeah, I take it everybody's seen this. I mean, it was everywhere. It was a landmark because it showed what was possible. But I don't know if people are so aware of how they'd solved this. So this is the setup they had. About 30 cameras, extremely large team who were all very well paid, and huge amounts of GPU resources, etc. So they've solved it by brute force. Do you know what happened to the team afterwards? Disbanded the team. Moved them all into ChatGPT and so on. They disbanded the team after this. So because there's no future in this, it's not scalable. Where do you go with this? So they got all the media attention, which is probably worth what they paid, to get this stuff to work. And then there's no future. But they're now obviously getting back into robotics with like Figure and so on. They're looking at humanoids for that. So they are following the rest of the herd now with the humanoids. So that's the end of that. And they say it's purely vision based, it's proprioception and vision based. That's how they solved it. No tactile sensing on this. So it's taken 3 or 4 years for tactile sensing to catch up. And then this is Meta AI who presented this. It's Jitendra Malik led this work. Howsey is the PhD student. Presented at Corel in November, December last year. So it's taken several years for the field to catch up to use tactile sensing, and tactile sensing is scalable because you can now use this for other things with the hand. And there's a couple of groups who can do this now, and so they've got something a bit like a gel site on the fingertips. Blurred it for confidentiality.
Is that using only tactile sensors? Is there no camera?
They used proprioception first. It's a fully actuated hand, and it can actually get quite good in hand manipulation with proprioception alone. This one actually uses tactile sensing and vision and proprioception. And it's unclear contributions of tactile and vision in this work. I don't think they separated that out, at least in reality, in simulation. It's using deep RL. It's using deep RL methods very similar to those that developed for controlling quadrupeds. So it's a student-teacher approach. I'll come back to this a bit later. So they've got gel site. There's some subtleties as well. They basically took the gel site into an 8-bit contact detector. So they don't use it in high resolution. They just segment it up into 8 pieces and then do binary 0-1 contacts on that. So they're not using the full high resolution tactile sensor. You'll see in a minute why I know a lot about this. But anyway, I say now the field has caught up in doing it the right way. So this is our experience with using deep learning. So pre-deep learning, we were using some sort of statistical methods, and we could kind of get some control, but it's quite rudimentary, as you can see. This is about 5 or 6 years ago. When we started using deep learning, 2018, 2019, this is the difference it made. Basically, the way this works is it's just a simple PID controller, and then you've got what we call a pose net, where from the tactile images, you predict basically the pose, the depth and the angle of the contact, if it was a flat surface, and if it's an edge, there's 5 dimensions of pose that you predict. And we have to do this trick where, because our sensor's soft, it's very sensitive to shear, So we basically had some form of data augmentation where we randomly put unlabeled shears into the when we're taking the training data, so that when the trained neural network becomes insensitive to the shear of the contact. That was the trick to get it working. And then you get very accurate results for the prediction, and that means that you can predict that PoseNet model into, you embed that into a conventional PID controller, and you can get quite general and quite robust control. And so this was just, in these cases of surfaces, it was just changed on the flat surface. Yeah, it's fine, noses and so on. That's kind of the magic of deep learning, and the fact that the sheer augmentation probably acts as a regularizer on the models and made them, more general and more robust. Okay, and then we push that forward to pushing. So goal-based pushing. So none of this is using fancy methods. This is all using basically PID controllers and neural network to predict things like pose. So this is again using the pose of the contact. It has proprioception, so it knows relative, where the end effector is relative to the target, and then you can use basically a simple PID controller to push something to the target. The Aruka marker is just for tracking, for validation afterwards. It's not used for the control. And the control looks something like this. So you've got a kind of servo controller, similar to we had for feeling over object, and then what's a bearing controller that kind of helps push it towards a bearing, which uses the proprioception. Okay, and so this is where we are now. The paper that's just been coming out in IGRR. So we extended it up to 3D. You can think of this a bit like 3D pushing. You're holding it. So this arm is following a preset trajectory, and then the other arm is called sticky fingers. Basically, it's just trying to keep, through touch alone, it's trying to keep the sensor on the object with basically and normal to the object. Absolutely critical to field shear for this to work, because you cannot, and this shows we're not cheating, you cannot do the rotatory movements, the sideway movements, you cannot sense that without shear. The pose is not sufficient on its own. If anything, shear is more important to sense than pose for this kind of task. Which is why, our sensor, say it's biometric, copies human touch. That's, I think, originally what human touch is more sensitive to shear as well. Probably for that very same reason. Once you've got this controller working, you can then, I said this is the controller. It did actually, John was a very good postdoc. To get this to work, it's got the kind of PID controller and the bearing controller, so like the pushing one. But we also, turns out shear is quite noisy. So we had to basically use a version of the Kalman filter to reduce the noise in those predictions, which required using a neural network that predicts both the mean and the uncertainty of the predictions as well. And then, because it's an SE3, the Kalman filter, we needed basically a Bayesian filter that works on non-Euclidean spaces, and that was, so there's lots of Lie algebra as well. This was a really good piece of work by John, getting this all working, which is what got into IJR. I say there is some sophistication in that. It's not easy at all, but say once it's working, it does kind of what you want it to do. So it does smooth. Some of the tasks we were doing before, it can still do, like pushing. But actually, before it was discretely pushing, and now it's continuously pushing. Same thing with the feeling surfaces. And then you can do things like use two arms to move things around. Just the tip of the iceberg. I think there's far more you can do with this type of controller than we did in the paper. But it's very difficult for anybody else to use this, actually. You need our sensor and then need the software structure, which, like I say, I'm happy to share, but it's not easy. And the gel site, I said, if it doesn't feel shear, it would be difficult to do, and it's not very soft. And the softness of the sensor is quite critical for this as well, because it's got a mechanical tolerance. Okay, so I'm going to show some more examples. So this is with the piezo IT hand. This is using a form of shear-based control as well. So not much seems to be happening here. Yeah, you're holding the cup lightly, an empty cup, pouring some stuff in, and then changes the mass of it, and then the hand will pour the cup. If you look closely, you'll see the fingers move a little bit. Yeah. But the point is, if you look at what the controller's actually doing, you can see the force, the normal force that's being applied varies between about 1 Newton and 5 newtons. So the forces are actually changing a lot under the controller, but it's doing what you want. It's keeping a stable grasp. It's doing the task. If it didn't do this, it would either crush the cup or drop it, basically. And so more obviously where the shear-based control is of use is this case, where you can guide the hand around. It's just using tactile sensing for this and feeling shear. And, you've got you can control the arm through the fingertips. Also, these are, as you notice, these are fingertips that's tactile sensor size of the human fingertip as well. These have got the £1,000 cameras in it, but as I say now it's £10 a camera. Okay, simulation graphics. This is what I'm going to wrap up here, so I should finish about 10 minutes. I was a bit sceptical about sim to real for Tactile a few years back. Ed may remember, I don't know. Basically because I thought Tactile was too hard to simulate realistically, and I thought if you didn't have a realistic simulation, it was pointless. This is what changed my mind. The student Alex Church, what he did is this isn't the same, it's not trying to faithfully mimic how our tactile sensor work, this is just giving a depth map. It's basically a CAD model, our CAD models that we use to 3D print it, put in the simulation with a depth camera inside, a virtual depth camera, and this is the image you get as it penetrates the surface. The point is the tactile images look are very different, and they say that this is shear based, that's indentation based, it's more like a gel side. But what we did is we fed it into the same PoseNet model, same controller, and then the CADs that we used for the experiments, we put them in and tried to get it to do the same thing. And so the behaviour was actually quite similar, how it worked. So this kind of changed my mind on it, because it means the problem isn't necessarily that you have to replicate the physics, the problem is you have to translate between this and that. To learn that, the sim to real translation, which is a supervised learning problem. So where you can do a lot of control in simulation, but the bit to map between real simulation and reality is supervised learning. So in principle that's simpler. So, and the point is, if you've got in simulation, then you can start using techniques like deep reinforcement learning that are very sample inefficient and aren't practical in reality because it takes thousands or millions of trials to learn. So these are some of the tasks which we could do already with conventional PID controllers, I've shown before, but now, say, learning a policy in simulation using RL. So you can do that in simulation, and then as I say, if you can learn to translate between the real image and the simulated tactile image, you can use the policy in simulation to control your robot. And then it works first shot. 0 shot, sim to real, just works. So this is a couple of years old. This was Corel 2021. This got published. We did try RSS, got rejected. So these things do. But let's say Corel 2021. So it's a couple of years old. But I say it works. I would say you don't actually learn much about how the policy is actually doing it. I mean, RL gives you a black box method. But yeah, as a method it works, and lots of other groups are finding that sim to real RL with touch is a viable method, and there's a lot of activity in the area because it gives you policies that work. That's what Meta AI did as well with the hand I showed earlier. And then I say students like this kind of thing, so I've had lots of projects doing this. So this is another example where using a low-cost arm, 2 low-cost arms together and doing like bimanual manipulation. Same methods. Let's say 2 robot arms, doing various things. Yeah. And you can kind of keep turning. If you've got a lab that's set up for doing this kind of thing, you can turn the handle on it and produce lots more papers, and the students enjoy doing this kind of thing. And that's kind of what's happened in my lab. And these are some more demos. So this one's actually using Course to Fine, inspired by Ed. So that's a combination of vision and touch. So I guess this is a bit of a microcosm of the field at large. There's a lot of labs doing this kind of thing and doing deep RL tuned policies for specific tasks. Okay, and then because it works at the end of the day, and it's not that hard. Once you've got the methods working. So other things you can do with sim to real is you can do object reconstruction. So 3D, there's been a revolution in 3D vision, as Andrew knows, for example, over these last few years, Gaussian splatting, NERFs and so on. There's there's a huge amount of activity and progress being made there. So you can start using those methods for reconstructing the shape of objects, but using touch instead. So what we did is we used a deep SDF, or what Marrow did, a deep side density function, basically a neural network that predicts how close you are to a boundary of an object. You can train it in simulation, because these things require a lot of training, a lot of the objects to train over, something like 50,000 objects, I think Marrow trained over. And then you are able to reconstruct from lots of little patches on the objects, the kind of thing up here, these local point clouds, you're able to reconstruct the shape of the object quite accurately, given little patches of depth maps on the object. So then this was based on work that Meta had done just before as well, using a digit, using a gel site. So what we did, we used the Tactile and used the same sim-to-real transformation as I was shown earlier. And then, you get just 10 or 20 taps on an object to little patches, you're able to reconstruct the shape of the object very accurately. I was amazed this worked, to be honest. But, there it is. The student actually doesn't think that Tactile is very interesting for 3D reconstruction and now just wants to work on vision. Which is a bit frustrating, but it's his PhD. So that's where this work has kind of stopped, to be honest, because he's now working on Gaussian splatting and so on. Okay, and now to finish the metas stuff. So, this is twiddling these objects around. It's using deep RL to learn the policy in simulation, and there's gel-like tactile sensors on it. All these different objects. Now, if you notice that the hand is always that way, the thing is not grasping these objects. What it's doing, many of the objects, it's actually just balancing the object on the fingertips, moving it around. And I think as well, they had to train different policies for the different, so it's rotating around different axes. So here, I think it's rotating around that axis. And I think there's a different policy trained for each of these different axes, rather than a unified policy. So the axis isn't fed in as an input. But you can see where I'm going here. So, as you notice, it's got tack tips on this Allegro hand, because we've picked up this work as well. Max started working on it April, May last year, is when we bought the hand. So we've moved quite fast on this. We've actually based it on work using a proprioceptive controller and then added our sense of touch to it. So it's a teacher-student kind of technique, which is basically there's privileged information used in the teacher, and then you state the object, etc., that you then remove in the student, so that this student policy can be used on real data. This is an example of the hand twiddling something around. The hand is upside down in this, as it's moving this object around the axis. And you see the complexity of the policies. These are the outputs it's producing. There's 4 fingers, 3 joints per finger. So it's 12 motors. I think it's actually 16 motors it's controlling on this hand. It's a 16-off hand. But you see, this is kind of complexity of the policies of the control you have to do to get this working. Okay, so this is the hand in a downward configuration, but rotating the object around different axes. Same policy for all of that. Now the hand in different orientations and different axes, still the same policy. This was really challenging actually, because not only because gravity affects how the hand works as well. The fingers have mass, and that causes a lot of issues. This is it doing lots of different objects, mainly because the reviewers at RSS asked us to do more objects. So here they are, if many of the reviewers are here. So this is it doing more objects. say different orientations, different axes, and then finally show off the hand moves around on an arm, twiddling the object at the same time. What I want to do, which Max is working on now, it won't be in the paper, but it's to keep the object in the same pose as the hand moves around. I think that would be quite a cool demo. So I see this as the start of a story rather than the end of a story. Meta didn't openly release either the code, and they kept secret the form of tactile sensor that they designed on it. We will openly release it. And so I think this is an important bottleneck to be going through, which in the field, so Meta obviously was there first, and then we've followed them with our technology. But once you've got something like this working, then you can start getting things like using tools, more general manipulation working. And so it'll be interesting to see where it goes in the future. I'm going to conclude this as 10 minutes of questions.
Yeah, okay.
Cool. Okay, thank you.
Nathan, thanks so much. Really, really great talk. Thanks a lot. Really nice to see that you're using some of my methods as well.
Oh, of course,
That was a nice surprise.
Yeah.
We have time for some questions, so if anyone has any questions, then there's your chance. Yeah.
Hello.
Hi, Nathan. See you again. I've got a quick question about the sim-to-real part, about the depth map. And the question would be, if you can already translate the depth map to the kind of the pin output, why don't you use the pin output in your training? Why do you still use the depth map?
Because we go from the pin output to the depth map. It's the opposite way around. It's actually quite difficult to go from the depth map to the pin output because there's missing information in the depth map.
Mapping from the...
You go from the pin output, the real readings, to the depth map. The simulation, in the simulation that uses the depth map. So the policy is using the depth map, and then the actions that come out, they can be used on the real robot.
Okay, that makes sense.
So we are working. There are advantages to doing it the other way around, as you say, of doing from the depth map to the pins, to the markers. But there's missing information. For example, a depth map doesn't have any shear information in it. Just as depth. So that means there's missing important information. So it is something we're currently working on. So you could do, as you're saying, then you could have a policy that works directly on the real tactile images if you can do it the other way around. Yeah, good question.
Hey, thanks again for a great talk. So also very interested in your sim-to-real work, and of course, as you said before, when you're designing sensor, there are many considerations, right, like cost and resolution, and I guess. I'm wondering whether ease of simulating a sensor is also a consideration that people think about, especially if you're going to continue this into your line of work, and how would you design it differently for future versions if you were going to make it easier to simulate?
Okay, so some people care about that. There have been papers where people have suggested sensors because they're easier to tactile sensors because they're easy to simulate. It's one way to go. The way things are going with the gel site, the gel site works as the gel site is. So, for example, NVIDIA are using that sensor is basically to put more and more physics into your simulation, so it becomes a more and more realistic representation of the sensor. That's their direction of travel. Our direction of travel is we're quite happy with it not being like reality, because you can learn to map between the two, and actually, if it's a supervised learning problem, you can have lots of data. You can learn about physics and everything that's missing in the model that translates between the two. So actually, I see it's more important to have quite a simple simulation that's kind of a cartoon of reality. Got enough physics in there that you can learn a policy that works, but actually to have the right gap to the real sensor. I said these are all different perspectives at the moment that people are working with. Maybe they're all right. Maybe
Yeah.
So at the moment it obviously does deformation really well. I'm wondering how much more difficult it is to look into texture. So more refined, maybe based on vibration and movement, dynamics. Have you looked into it?
Well, we do have versions of our sensor which can feel vibration as well. You can put, a microphone in the gel, and then it will feel vibration. So we've done that. So in terms of technology, you can do it, and then there's various ways of doing that as well. How you would then use that in simulation, we haven't looked at. Texture is important. The most important thing from texture, if you're looking at dexterity, is things like friction and being able to predict friction. Well, if you can determine friction, then you can do things like predict when things are going to slip. So that for sure will come in the future, but I don't think the field's there at the moment.
Andy?
I was thinking something your sensor should be good at would be like really kind of loose grasps and things like that. I mean, I guess doing quite fast sensing, the sort of things humans just do. You flip your phone out and you kind of rotate it. I don't know. I haven't seen robots doing things like that, but that sort of ability to measure shear and that really kind of light touch and stuff would seem to be a really good fit. I wondered if you thought that, tried anything like that, or.
Yeah, I mean, so we haven't tried. I mean, I agree. Yeah, I mean, we're very sensitive to small forces and sensitive to slips and controlling shear, and so I think you're right. I mean, why haven't we tried it? I guess we just haven't thought of it.
Because everyone else just does rotating, so it's like you've got to compare to their benchmarks or whatever.
Yeah. Gel sites are never going to be able to do that.
Yeah. There was a paper called Tossbot.
Tossing
Where they were kind of
Throwing and catching, I was thinking, something like, let's say, releasing a dart or something. Timing that release is really hard, or catching as well. There's like a soft catching or something.
Yeah.
Those would be brilliant.
Well, I agree. That's probably where the field's going to be.
How fast can you sense it? I mean, it's the rate of the camera, I assume.
Exactly.
There's no reason why that shouldn't be really fast.
Yeah, I would say that the limitation about we can't do more dynamic.
Yeah.
So all the manipulation there was kind of quasi-static, single images, and not really using the dynamics of it. I do think that's probably where the field's going to be going, towards more dynamic manipulation. But not many. It's hard to get to because you've got to have the sensors, you've got to have the infrastructure, and you've got to have the hardware. So yeah, I mean, I imagine that's where it will go. And as you say, things like the camera latency. That's going to be important. But also the control latency. So the stuff that was most closely related to that was where the slip experiments, where it would hold something and then basically loosen the hand until the object slipped. Actually, this has got a bit of something left in it. So. Loosen the hand until it slipped, and then it had to recatch it. So that's the closest we did there. So it had a really simple slip detector, but it worked. But the student worked really hard on getting the latencies in the control loop down to sort of 15 milliseconds or so.